Today, we are very glad to make this video for our team project of this machine learning course. The title of our project is called What's Cooking? Our presentation is divided into 6 parts: introduction, data exploration, data pre-processing, model construction, model ensemble, and conclusion. First, I will give a brief introduction of our data. In the dataset, we include the recipe ID, the type of cuisine, and the list of ingredients of each recipe of variable length. The data is stored in JSON format. An example of a recipe node in train.json is shown in the right. We have two files. Train.json is a training set containing recipe ID, type of cuisine, and list of ingredients. Test.json is a test set containing recipe ID and list of ingredients. Our objective is to accurately predict the category of a dish's cuisine given a list of its ingredients. Some of our strongest geographic and cultural associations are tied to a region's local foods. People can make use of the prediction to find something fun. The second part is about data exploration. When we get the datasets, the first thing we should do is to know our datasets well, so we can use visualization method to explore the data and find some useful pattern. First, we draw a distribution histogram about ingredients in a dish as below, and we can easily find that most dishes have 5 to 20 cans of ingredients. Then, we try to find the ingredients which are used in most of dishes and draw a bar chart about the top 15 ingredients. Salt, olive oil, and onions are top 3 ingredients that most dishes use. Thirdly, we want to find the cuisine's distribution in each country and find that most dishes come from Italy, Mexico, and southern US. Then, we choose the top 3 countries in previous cuisine distribution and our country China to find the most frequent pair of ingredients in these countries. Finally, we draw top 25 diagrams for any 2 countries to find their relationship. Taking Thai and Chinese for example, we can find that both of them like using chicken and broth to make dishes.
In the data preprocessing part, we are going to follow these 6 steps. First, we remove the non-alphabetic characters, which contain some unnecessary details of ingredients. For example, we remove the exact fat percentage of the low-fat milk. Second, we use WordNet lemmatizer to get the singular form of each ingredient, assuming that only the variety of ingredients matters, rather than the amount of each ingredient. Third, we remove some stop words such as the or and, because these words are presumed to be uninformative in representing the cuisine. Fourth, we applied TF, IDF to the unigrams of ingredients. TF stands for term frequency, which is the occurrence frequency of a term in a document. IDF stands for inverse document frequency, which is a measure of how much information the word provides. For example, according to our previous data exploration, the ingredient salt is really common among all the dishes, so its IDF value will be relatively low, which means that it doesn't provide much useful information in predicting cuisine. Then we multiply TF and IDF to get the TF-IDF value of each unigram. The unigram with higher TF-IDF value is considered to be more important in predicting the cuisine. Fifth, we use hashing vectorizer to convert the unigrams as well as the bigrams to a matrix of normalized token frequencies. The reason of choosing this method is that the number of bigrams is quite large, and hashing vectorizer is very low memory scalable to large datasets, as there is no need to store a vocabulary dictionary in memory. Though there is no way to compute the inverse transform, it doesn't matter in our prediction task. Finally, we combine the unigram features as well as the bigram features together using the feature union method.
This part, we'll talk about the model construction. Because our project fitting the high dimension problem, after we do the DF-IDF job, we got the matrix over 9,000 dimensions. So, firstly, we do the decreased dimension job. We choose to use principal component analysis. PCA's score is to maximize the variance of projected data. The right parts of the slides tell the details of PCA, but fortunately, sklearn's package have achieved it. So we just use the sklearn's package to achieve it, like this picture showed. About the base models, we use multi-class logistic regression firstly. Just as we taught in class, it is based on the possible model as showed below. And actually, it is the enhance of logistical regression. So when the number of class is 2, it is the same as logistic regression. And it also updates the parameters by gradient descent as the third formula showed. We achieved it based on the package of sklearn2, as this picture showed. We do 5 folds and the mean accuracy is about 0.77.
And next, to complete the classification task, we also choose to build up a random forest classifier. Random forest classifier is based on traditional decision tree classifier. A decision tree is a flowchart-like structure in which each internal node represents a test on an attribute. For example, whether a cuisine includes yellow curry. Each branch represents the outcome of the test, and each leaf node represents a class label. The paths from root to leaf represent classification rules. As shown in our slide, the logic behind a decision tree classifier used to solve this classification problem is quite clear, since the features we have are all 0-1 categorical data, which stands for whether there exists an ingredient in a cuisine. However, a single decision tree may easily lead to serious overfitting problem. Using random forest instead of decision tree can help us solve this problem. Random forest classifier uses bagging methods to ensemble many decision trees and use an aggregation function or faulting to get the final prediction. Bagging is short for bootstrap aggregating. In a bootstrap process, we draw many bootstrap samples, and based on these samples, we train different models. And based on this, random forest goes further as a refinement of bag trees. At each split, a random sample of m features is drawn. Only these features are used to do the split so that we can get different trees to help us do the classification. We use our raw data to build our model and get an accuracy of around 0.65, which is lower than what's expected. Because during the experiment, we encounter memory errors when training the model, no matter on our local Python system or the online machine learning platform provided by Google, because the memory required by random forest is quite large when fitting a data with both high dimension and a large sample size. Seeking for a solution on it, we turn to LightGBM for higher memory efficiency. LightGBM is a gradient boosting framework that uses tree-based learning algorithms. It is designed to be distributed and efficient with the following advantages shown in the slides. This model is also a decision tree algorithm based on histogram, using a leaf growth strategy on leaf-wise with depth restriction. Its advantages are mainly achieved by histogram difference acceleration, direct support from categorical features, and catch-hit ratio optimization. The accuracy of our LGB model is around 0.71, and we can get a result within 10 minutes with this model, which is quite efficient.
Linear SVC, linear support vector classification, is similar to SVC with parameter kernel equal linear, while there are still some differences between linear SVC and SVC. Linear SVC minimizes the squared hinge loss, while SVC minimizes the regular hinge loss. Linear SVC uses the one-verse-all multi-class reduction, while SVC uses the one-verse-one multi-class reduction. Linear SVC uses lab linear rather than lab SVM, so it has more flexibility in the choice of penalties and the loss functions. Also, it should scale better to a large number of samples. As our data volume is large enough, the linear SVC might perform well in our data. Meanwhile, L2 penalty is used to prevent overfitting. After applying TF-IDF, our data is in high dimension and has a large amount of samples. Linear SVC could perform well on it. After using grid search CV, penalty coefficient C is set to 0.5 because the amount of samples is larger than the amount of features. Parameter DUAL is set to false. Applying the model on testing data, the classification accuracy is 0.794, which is a good performance.
Finally, to enhance our model, we use two-layer stacking. The theory of stacking is just like the left picture showed. We let linear SVC, random forest, and let JBM to be the base models and do 5 folds, like the softmax regression as a met model. After we doing enhance, we got the final accuracy to be above 0.8. In summary, this is what we did. First, do data exploration a job. Second, do TF-IDF to reflect how important a word is to a quizzing. Third, do PCA to decrease dimensions. Fourth, achieve several base models, include softmax regression, random forest, JBM, and linear SVC. Finally, do stacking to enhance the result. That's all, and thanks for listening.